Hello everyone, hello Professor. In today's video, I'm going to introduce you to another lesson from chapter 10, which is subchapter 10.8, Taylor and the Maclaurin series. So let's get started. So as we have already learned with the previous subchapter, which is 10.7, we have already learned about the power series. So the power series is a series in the form of the following: C sub n times x to the power of n. We mentioned that the sum of the power series can be represented by a function in term which involving each of the power of x all the way to the infinity. And this is the expanded form of the summation of the power series. So we may want to know more on these coefficients. As we already understand the differentiation, we are ready to expand our understanding of this series. So without further ado, let's get right into it. So let's say we have the summation of n equal to 0 to infinity of c sub n times x minus a to the power of n. We can write this summation as an expanded form as f of x equal to z0 plus c1 times x minus a plus c2 x minus a to the power of 2 plus c3 times x minus a to the power of 3 plus and so on. So if we evaluate f at a, these binomials will become 0. Therefore, the rest of the term will become 0. So what do we have left? We have c0, which is our first coefficient. So f of a equal to c0. So how do we find the next one, which is c1? This is when the differentiation comes to play. So if we do the first derivative of the function, we will get c1 plus 2c2 times x minus a plus 3c3 times x minus a to the power of 2 plus 4c4 times x minus a to the power of 3 plus and so on. So if we want to evaluate f prime of x at a, these binomials will become 0 again. So all of these terms will become 0. And what do we have left? We have c1. So we have f prime of a equal to c1. So how do we find the next one, which is c2? In order to find c2, we have to do the second prime of x, which is the second derivative of the function. So if we do the second derivative of the function, we get 2c2 plus 6c3 times x minus a plus 12c4 times x minus a to the power of 2. And again, if we evaluate f at f second prime of x at a, we will get 2c2 because these binomials will become 0. So we have f second prime of a equal to 2c2, or we can write as c2 equal to f second prime of a over 2. How do we find the next one, which is c3? So we have to do the third derivative. So the third derivative of the function equal to 6c3 plus 24c4 times x minus a plus and so on. So we have to repeat the evaluation again. We have to plug a into the third derivative. So we evaluate the third derivative of the function at a. We will get the f third derivative at a equal to 6c3. Or we can write as c3 equal to f third prime of a over 6. So we can see the pattern here. So we can assume that the f fourth prime of a will equal to 24c4, or we can write as c4 equal to f fourth derivative of a over 24. So as you may see that this here is number 2, here is 6, and here is 24. Or we can write it as the factorial number. So we can write as 2 factorial, and here we can write c3. At c3 we can write 3 factorial, and at c4 here we can write the 4 factorial. Okay? So now we can assume at cn we will have cn equal to f of n prime of a over n factorial. Right now, we can plug this Cn into our summation of the summation above. So here's the summation. We get the summation n equals 0 to infinity of f n derivative of a over n factorial times x minus a to the power of n. So this is the Taylor series that we have found. So basically, the Taylor series is born from the summation of the power series. Okay? So let's talk about the special term. So the special case of the Taylor series is when a equal to 0. So if we plug 0 in there, we will have the summation of n equals 0 to the infinity of f n derivative of 0 over n factorial times x to the power of n. So this special case, we can represent this summation as the another series, which we call the Maclaurin series. So there is no any difference between the Maclaurin series and the Taylor series. There isn't much different because the Maclaurin series is just a special case from Taylor series. Okay. So let's talk about the Taylor polynomial. Taylor series is very useful in linearization. With Taylor series, we can approximate a very complex transcendental function with the series of a simple algebraic function. So the first order of the Taylor polynomial is P1 of x equal to f of a plus f prime of a times x minus a. This is just the equation of the tangent line at the point x equal to a. So when n increases to 2, we get the second polynomial function. So P2 of x equal to f of a plus f prime of a times x minus a plus f n prime of a over 2 factorial times x minus a to the power of 2 and so power of 2. So P2 is a quadratic function. P2 of x would approximate the value of the function of the graph at that point better than P1. So if we keep increasing the number until n, we get the P of x equal to f of a plus f prime of a times x minus a plus f of n of f prime n prime of a over 2 factorial times x minus a to the power of 2 plus so on until f n prime of a over n factorial times x minus a to the power of n. And we can assume that p of x equal to p sub n minus 1 of x plus f n prime of a over n factorial times x minus a to the power of n. So let's talk about the example 1. Find the Taylor series for the function natural logarithm of x centered at a equal to 1. So in order to find the Taylor series for this function, first we need to find the first 4 differentiation of this function. So the first 4 of differentiation of this function is this. So the first derivative of this function equal to 1 over x. The second derivative equal to minus 1 over x squared. The third derivative equal to 2 over x cubed. The fourth derivative equal to minus 6 over x cubed. Next, we have to plug the value of a. We have to evaluate these functions at a. So if a equal to 1, at f of 1 equal to 0, f prime of 1 equal to 1, f second prime of 1 equal to minus 1, f third prime of 1 equal to 2, f fourth prime of 1 would equal to 6. So let's substitute these answers into our formula. So our formula, this is a summation of the Taylor series, and we can write it as the expanded form, f of a plus f prime of a times x minus a plus f n prime of a times x minus a to the power of 2 over 2 factorial, plus and so on. So we plug the value in. We do the calculation in this, and we would get fx equal to x minus 1 minus x minus 1 to the power of 2 over 1 times 2 plus 2 times x minus 1 to the power of 3 over 1 times 2 times 3 minus 6 times x minus 1 to the power of 4 over 1 times 2 times 3 times 4 plus and so on. So in this case we can evaluate this 2 and 2 here, and 6 and 2 times 3 would be equal to 6 as well. So we can evaluate these two, 6 and 2 and 3. We get f of x equal to x minus 1 minus x minus 1 to the power of 2 over 2 plus x minus 1 to the power of 3 over 3 minus x to the power minus 1 to the power of 4 over 4 plus and so on. And from here we can write as the summation of the expanded expression. We get the summation from n equal to 0 to infinity of the minus 1 to the power of n times x minus 1 to the power of n plus 1 over n plus 1. Let's do the example 2. Find the Taylor series for the function e to the power of x centered at a equal to 3. So the same thing, we have to find the first 4 differentiation of this function. So the first 4 differentiation of this function is here, these. So no matter how many you're gonna do the derivative of the function of e to the power of x, you will still get the same answer, which is the e to the power of x. So let's plug the value of a in. We will get the same answer as well from f to the fourth prime f of 3, we get the same answer, e to the power of 3. So let's plug this value into our formula. So here we're using the same formula. So if we plug in, we get the f of x equal to e to the power of 3 plus e to the power of 3 times x minus 3 plus e to the power of 3 times x minus 3 to the power of 2 over 2 factorial plus e to the power of 3 times x minus 3 to the power of 3 over 3 factorial plus e to the power of 3 times x minus 3 to the power of 4 over 4 factorial plus and so on. And we can write it as the summation in short form as the summation from n equal to 0 to infinity of 3e to the power of 3 times x minus 3 to the power of n over n factorial. So let's do the example 3. Find the Maclaurin series generated by f of x equal to e to the power of x. So in order to find this, you have to do the same thing, find the first 4 derivative of this function. But as we already know that no matter how many times we do the derivative of this function, we will still get e to the power of x. So f n prime of x equal to e to the power of x. And as we already know that Maclaurin series is a special case one, that a will be equal to 0. So f n prime of 0 equal to e to the power of 0, which is equal to 1. So this is the formula of the Maclaurin series. So we just have to plug the value in, and we can get the fx equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial plus and so on. So now let's do the approximate value of the integral 0 to 1 of e to the power minus x squared dx. As we know that e to the power of x equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial plus and so on. So if we do the integration from 0 to 1, we get the x minus x cubed over 3 plus x to the power of 5 over 5 times 2 factorial minus x to the power of 7 over 7 times 3 factorial plus x to the power of 9 over 9 times 4 factorial minus x to the power of 11 over 11 times 5 factorial plus x to the power of 13 over 13 times 7 factorial plus so on. And we get the 1 minus 1 over 3 plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus 1 over 11 times 5 factorial plus 1 over 13 times 7 factorial plus so on. And we can have our approximation of the integral from 0 to 1 e to the power of minus x squared dx would, as estimation, we get 0.7468. And that is basically for this video. I hope you guys enjoy. Thank you for watching. And I'll see you in the next video, hopefully.